Hi, welcome everybody to our 25th How to Repair Pendulum Clocks Open Clock Club. And it's been, as always, it seems to always be a busy old horological week. So really happy about that. Particular warm welcome to beginners and people who have joined us for the first time. What we do here is thinking on his feet. What we did here was write a book. John, who has joined us this evening, and me spent years writing a book to help beginners get off the starting line with either a hobby or the profession of clock making and clock repair. And we decided to run some support events where we built up a kind of community. And that's what this is essentially. So we run these events every Saturday for a year, we promised, and we're about halfway there now. And then we also run a thing on a Thursday evening. You're very welcome to join us on YouTube for a live stream of fixing a long case clock, tall case clock. And we also have passed 300 members on our Facebook group this week. It seems to be going like crazy, and no wonder, because it's such a great, healthy, I think, friendly place where there's such a lot of amazing information exchange. So the Facebook group has really kind of got its own life now, and so those people who are regular contributors, I say this every week, but a heartfelt thanks to you, because without you people chipping in at all times of night and day, it wouldn't work. And I think what's great about that group is that it is pretty tightly focused on clock repair, obviously, and things like tools, bit about lathes, but basically people's projects and problems they have and successes they have. And we go off on a bit of a tangent onto dials and things a bit as well, but it's really cool. So thank you all for doing that. As you can see on the bench, my housekeeping note, remember, please, particularly if you're the first beginners here this evening, that these sessions are recorded, and the recording does go, and I always have to check whether it's recording. Yes, it's recording. The sessions do go on our YouTube channel. So if you like what you see here, then please look back through our archive, which is getting pretty substantial now. It's getting a bit crazy. I've slightly forgotten the beginning of this whole thing, but nice to see you anyway. So on the bench in front of us, you can see what the beginning of all this trouble. That's a Smith's Enfield single train mantle clock movement, or clock movement. And we're going to be talking about this a bit later on. We are going to kind of, we've had a few weeks where we've been off on a tangent, and we're going to go sort of back to basics, and we're adjusting the escapement at the moment, and we're going to put the clock in beat. A lot of people say, you know, as a beginner, how do you get the clock in beat? What does that mean? So I'm going to demonstrate that, and we're going to stick the clock in the case. A slight panic because I've forgotten where the case, it's there. Oh yeah, I remember now. In the case, which is all ready and vacuumed out and cleaned. We'll talk a bit about that as well. But before that, last week, and please bear with us, I'll just unhook the pendulum, by the way, when you move a mantle clock, if you can. Last week, we did some drawing. We had a Facebook participant who bought a clock and it had no pallets. The pallets are kind of one half of the thing called the escapement, again, for beginners. It's in our book, by the way. And those pallets were missing. So the really great question was, how the heck do you go about designing pallets? And so we did that last week anyway. So if you want to see that, go to the archive version of it. But he said, we see if it's going to focus. Maybe we'll have to just, I see. There we go. We got some questions about it, which was brilliant. And a few of those questions were about the kind of drawings that you tend to see in clock repair books, and in particular the book by Gaisley. I think one of our Facebook people said, I've got Gaisley, and Gaisley draws those pallets with curved surfaces. So brilliant, let's answer that question. Why, Matthew, did your pallets, and if I could find them, I would show you, but I've lost them under a mountain of junk here, but I can easily draw them again. As you know, if you joined us last week, they're the easiest thing in the world to draw. No, they're not quite, but so here's a drawing that was provided by one of the person that bought the clock that had no pallets. And cut a long story short, we essentially said that one pallet is going to end up like this, and one pallet is going to end up like this. And what, of course, I didn't do last week, somebody said, it was really great, Matthew, and so I was really pleased when you drew the pallet body in. The pallet faces essentially were developed from our escaping angle and our impulse angle. Again, it's all there from last week's session, but I thought what I should have done as well is I drew a kind of European style long case clock, tall case clock pallet frame. But if you've got strip pallets, so the bent round type, like we've got on our Smith Enfield clock, or like on a lot of American clocks, then exactly the same. All we're interested to hear is our pivot point, and which is the pallet arbor, the axis about which the pallets reciprocate, and our working surfaces. And if you've got strip pallets, so a strip of material that's bent round, it's exactly the same thing. So don't worry. Escape wheel's going in this direction. So we've got clearance here. Ooh, dodgy drawing as always, and clearance back here as well. So you can see that whether it's the solid type pallets or the strip pallets, it makes no odds, same difference. But so the key thing was, and I've got plenty, lots of copies, I think, is this difference. Oh, and by the way, I got rid of my book by Gaisley on escapements. I didn't find it at all useful. So I don't know whether it's arrived yet went to California. So that was really cool, really enjoyed that. So here are our pallet faces, whether they're strip pallets or the solid type pallets. And somebody wrote in and quite rightly said, well, wait a minute, Matthew, in Gaisley, he or they or whoever it was draws those as curved surfaces. What's that all about? Should I have curved surfaces or should I have these? So curved surfaces like this, or should I have these straight surfaces that you've drawn? Well, the answer is that we've got bleed through. Let's just move that off, then that'll prevent further bleed through. The answer is it depends what you want, really. The straight surfaces are fine, absolutely work fine, but really for weight-driven clocks like our long case clock. And the reason for this is to do with escapement error. Now, you might have heard in the first thing that clock students, John was telling me this story the other day about Galileo sat in the cathedral at Pisa, timing the swinging lamps against his pulse and all that stuff. Apocryphal or not, we don't know, but it's a great story. And what Galileo didn't realize, of course, was that he, named, I don't think named it, but he said that the arc or the period of these lamps was isochronous. They keep equal time irrespective of their arc, independent of arc or independent of amplitude. And of course, Huygens, Christian Huygens, a great Dutch mathematician, famously said, no, that's not true. For your pendulum to keep equal time, for it to be isochronous, so depending whether it swings a little bit or a lot, it doesn't swing in a circle, it swings in a cycloidal arc. And clock people call this circular error. So you've heard of circular error. You've probably heard of other errors like temperature compensation with the work of people like John Harrison and George Graham and John Ellicott, developing clocks that ran the same time irrespective of temperature. So our clock and our escapement and our pendulum are subject to a whole range of errors. And one that people don't seem to know about much, but is really important, particularly for spring-driven clocks, is escapement error. So what is escapement error? I can hear you all asking, please tell me, Matthew. So the anchor recoil escapement has got a positive escapement error. Now, we don't normally see this because it's regulated out of our clocks. But in answer to the question about why are the pallets curved on some clocks, why does Gaisley draw them curved, is to deal to a degree with this positive escapement error. Again, our Facebook correspondent said, you know, my clock gains like crazy at the beginning of the week and then it slows down. Well, all spring-driven clocks with anchor recoil escapements do, but it's particularly pronounced in this case because, of course, the mainsprings have been replaced. So my advice was put the old mainsprings back in, even if they appear set, whatever that means. So what the heck is escapement error? So let's just take our pendulum here and just get in focus, which would help. There we go. Hopefully that's sharpish there, sharpy. So draw a center line. I'm drawing at an angle, but actually, just move that across. Actually, this is the point at which the pendulum would hang if it wasn't swinging, if it wasn't oscillating. This is basically gravity pulling it down towards the center of the Earth. So that's our point of rest. So let's draw our pendulum in there. We'll draw it at rest. So here's our suspension spring. Here's our pendulum. And there is the bob. So that's its normal position, point of rest. Of course, when the clock is running, then it has amplitude. And last week or the week before, we talked about, and also in our book, we talked about escaping arc and supplementary arc as well. Check the microphone's on. So what you might want to do is to start the clock running by just giving the pendulum a little push so it doesn't tick, and slowly building up amplitude to the point where the pendulum ticks. And we call that escaping arc. That's a minimum amount the pendulum needs to be displaced or to swing for the clock to tick. So let's just draw that in. Let's call something like that. So this green hatched area here is called escaping arc. Okay, cool. Now, a clock doesn't actually run like that, or a pendulum clock like this, because if it ran only at escaping arc, then, and we're just going to concentrate for the time being on the pendulum swinging in one direction only. So through the line of centers to this point here, the same applies in the other direction, but let's just deal with this for the time being. If we only had escaping arc, then the problem is that the clock wouldn't actually run, because the slightest deviation in power, or somebody slamming a door, or whatever it was, a wind blowing on the pendulum, and the thing wouldn't reach the point where it escaped and the clock would stop. So we need some extra amplitude over and above that. Let's go for blue. Let's just draw that in here like that. And this bit, those zones, we'll call supplementary, running out of space, arc. Okay, supplementary arc. So this is all important, and it's related to this issue about the pallets having flat bases or curved bases in relation to spring-driven clocks. That's clocks where the driving force changes as the duration of the clock goes on. It applies to weight-driven clocks as well, but we don't see it because it's regulated out. And other than the sinusoidal effect of gears engaging and disengaging, again, we don't really see that because, again, that's averaged out. But we do see it on spring-driven clocks that don't have a fusee. So escapement error. What we've got here is we know that our anchor recoil escapement pushes the pendulum before the line of centers. So in this kind of area here. And here we go. I'll do another drawing that hasn't got these zones on it. Now we're used to the concept of escaping arc and supplementary arc. So let's just redraw that. I'll try and use the same colors. Point of rest. Escaping arc. Drop my pen and supplementary arc. Okay, let's just draw a center line down there so we know that's our point of rest. If our pendulum or any oscillator like this gets a push, more energy into the system, before this point of rest, in the case of a pendulum, it's going to, if you imagine this was somebody sat on a swing and you push them, remember our pendulum, as far as we're concerned, is only moving in this direction for the sake of this demonstration. If this person here was a person on a swing, you give them a push, they would reach this point quicker than they would if it were for gravity alone. So effectively, we're adding to the value of gravity. So if we draw in here, being pushed like this, we can put a plus sign there. The opposite happens if we push after the line of centers. So if we push in this direction, same direction, after we've passed this point of rest or the neutral point, then we make that period longer. It takes longer to get back to the same position. So we're effectively reducing gravity, if you like, for if you bear with me there. And so any push to your pendulum after the line of centers is going to result in a losing rate. And the opposite applies with a retarding action. If we're pushing effectively in the other direction, as we'll see in a minute in recoil, so if we have a retarding action, pendulum is still swinging in this direction, we've got a retarding action here, it's going to take our pendulum longer to reach this point of rest. And the same thing here, if we have a retarding action, it's going to be quicker to get back to the same point. So we can see before the line of centers, additional energy is making the thing faster. After the line of centers, additional energy is making it slower. Before the line of centers, retarding is making it slower. After the line of centers, retarding action is making it faster. So on something, if we've got like a chronometer escapement, for instance, where people are obsessed about the action being through the line of centers, those things equal themselves out. Energy before and energy after, either addition, or subtraction, equals the same thing, and it appears to be equal timekeeping. But if we move on, bear that in mind, this is escapement error we're talking about, and a bit of bleed through. Let's go back to our pallet faces. Now I drew them last week as, just to keep life simple, one horizontal face and one vertical face. Let's draw them the same length. And somewhere up here, we've got our pallet arbor like this, and I can draw them in if it still doesn't kind of make sense. I've squished them together for the sake of this drawing, but let's just quickly draw them in. Here's our pallets. Never seen pallets like that before, but anyway, or you could have strip pallets like this. It doesn't make any difference. So there's our pallets. We've got an entry pallet here, an exit pallet here. It's all in our book, not escapement error, but the kind of geometry of the escapement. So these two blue lines that we're interested in. Now we know that our active escape wheel tooth and in an anchor recoil escapement, at any one time, we've only got one tooth that's doing the work. So let's say that tooth, it's been in external drop and it lands here on our pallet face. Okay, it's going to then impulse the pallet and the pendulum by rotating it in this direction counterclockwise as we're looking at it, until the pallet effectively reaches this point, the sort of discharging corner, if you like it, of our pallet. And that same active tooth is going to land on here. It's going to slide along and it's going to land on here. Now, given that, let's just draw an internal and external drop. So this is internal drop, and external drop is all the way around like that. Okay, we've talked about this before. Happy to go over it again next week if we need to do. So this in itself, in its own, isn't a problem about escapement error per se, because at some point between this point and this point and this point and this point, the pendulum passes through the line of centers. I think I haven't really figured it out, but let's say for sake of argument, this is the line of centers. This is the line of centers. So half that impulse is before and half is after the line of centers. And as we've just heard, what you gain before, you lose after, very broadly. So this is kind of neutral. However, that's not all, is it? Because remember, on our escapement, we've got, get the right drawing, on our escapement, we've got supplementary arc. So when our pallet, escape wheel tooth, sorry, lands on the base of the pallet, whether it's the entry pallet or the exit pallet on the anchor recoil escapement, we get recoil. So the escape wheel tooth doesn't immediately start going in this direction. What it does first is it moves up the pallet in the other direction. Recoil takes place. So I've drawn the extent of recoil in there. This is our supplementary arc that we just talked about. And here is the problem, because you may remember from the drawing a few minutes ago about where you put energy into the system in relation to gaining and losing. Think about this. So first, we've got a retarding action going in this direction. Then we've got an extra bit of impulse going in this direction. And both those actions are accelerating the rate. This is the primary reason why the anchor recoil escapement has got a positive escapement error. So as the pendulum is working against the escape wheel, or the escape wheel is working against the pendulum in the first half of, in the first part, which is the recoil bit where the hands and the wheel train goes backwards, the action is being retarded. And because that's at that side of the escapement, that is a gaining rate. It's getting back to the same point quicker, effectively. And then we've got this double whammy of impulse, that in fact, we've got impulse all the way along here, and impulse all the way along here. We've already dealt with this bit, but this bit and this bit are extra. And that is why you want to radius that pallet face, because if you go here, and rather than having this as a straight line and this as a straight line, if you begin to, it would actually be like this, wouldn't it? Curve this back, and let me get this right, curve this back, it limits or reduces the amount of retarding and advancing action in the recoil phase, and therefore it reduces escapement error, positive escapement error. And this is not a problem on weight-driven clocks, as I've seen, because it's regulated out, you don't see it. But if you've got a clock that doesn't have a fusee, and at the beginning of the week, it's been driven much more than it is at the end of the week, for instance, then radiusing the pallets like this is going to help reduce escapement error. That's basically it. Don't replace your mainsprings just because they're set. That's going to make things a whole lot worse. And if you're making a new pair of pallets for a clock and you've got a free hand with the design and it's a spring-driven clock without a fusee, then you probably want to do this. And if you take it to extreme, my drawings get a bit scruffy, I'm afraid. If you take it to extreme, here's our pallet arbor look. If we put this part of the escapement as a constant radius to that pallet arbor, what do we have? we've got deadbeat escapement, or what we saw Dale a few weeks ago talking about, the half deadbeat escapement. So a little bit of a scruffy drawing, but hopefully that helps with this thing, because most people, as I said before, have heard about temperature compensation, that error. They've heard about circular error through the work of Huygens, and those clocks with cycloidal cheeks, which is what's that about. Most people have not heard about escapement error. If they have, it's kind of difficult to get your head around it. So there you go. If you've got a microset timer on a weight-driven clock, for instance, if you put more weight on, you'll see that the clock gains time. If you take some driving weight off, you'll see that it loses time. Or in fact, if you've just got a clock with no weights on, anchor, recoil, escapement, put your finger on the center wheel and give it a good old shove, you'll see that the pallets wiggle like crazy because of that escapement error. And the harder you push, the quicker they go, basically. So anyway, back to the rest of the meeting. So yeah, if you're designing a clock, and it's interesting now we've discussed this, or I've ranted on about it, when you look at clocks, you'll go, right, on a weight-driven clock, you can just have straight pallet faces because your driving force is the same. As long as, apparently where John lives, he has to get up and measure the local value of gravity every day because it changes such a lot. But for most of us on planet Earth, it's the same every day as far as we're concerned. So our weight-driven clocks, you don't see escapement error. You regulate it out when you first set up the clock and get it going, and then you never see it as long as the weight remains the same. You do, however, if you've got one of those microset timers or an app, I forgot the name of the app. Can somebody put it in the live chat, please, John, if you're there? It is again in the book, because there's a really cool thing, and I must stop banging on about this and start talking about something else. But even on a weight-driven clock, if you hook it up to a microset timer or to one of those clock app timer things, you'll notice that the clock doesn't keep equal time. If you're to track the time, you've got a pretty sort of low frequency thing like that, and then you've got a higher frequency thing like that, and then you've got a very high frequency thing like that, and they all compound together. You obviously got one line, and that's because of the sinusoidal action of the wheels and the pinions engaging and disengaging, feeding different power, different torque to the escape wheel, which is manifested as escapement error as well, and a little bit of circular error, but that's a relatively small value. So when you see on your microset timer the thing going up and down, it's because you've got an anchor recoil escapement, I think. So one from Chris, these are questions, by the way. Is the anchor recoil more resistant to uniform something than the deadbeat, where this is written down in, what's that word?
More resistant to error from excess swing than the deadbeat. And do you know a reference for it?
It's a good point, Chris. I'll just right, okay. Oh gosh, some really good questions. So Chris asked about the anchor recoil escapement and the deadbeat. I think the question was about, is that a question about circular error, Chris? Yeah, about amplitude. Right, this is like, oh, you can see our questions now. I will put those there. Just in case Rachel's written anything like she does. Anyway, this is one of the crazy things in neurology. You know, I've got a bit of a downer on clock books, apart from ours, of course, from Daniels and John Wilding and Malcolm Wilde. They're 4 really great clock books, because the same old stuff gets perpetuated in these books. So one of the best questions in any profession is, really, is that right? You know, who says that's right? Mainsprings being set, where does that come from? Who said it? And another thing is that the deadbeat escapement is a better escapement than the anchor recoil escapement. I don't think it is. Jonathan Betts carried out an experiment at Greenwich, and some of you have been to that workshop will have seen it. That he took a regulator by Cook of York with a deadbeat escape wheel, and a student made a pair of recoil pallets And so they were screwed onto the pallet arbor, changed them like for like. And the clock ran just as well. Basically, we're used to clocks with deadbeat escapements, at least in Europe, where the train's better, the pendulum's better quality, I think it's compensated or something. The whole thing's bolted to the wall. They're the reasons why the clocks keep good time. That I think that this whole thing about the deadbeat escapement being better, given uniform driving force. Yeah, if you've got non-uniform driving force, then a deadbeat escapement, because the negative escapement error is relatively small compared to the recoil, is going to be better. But as Harrison proved with his regulator, this whole thing again about circular error doesn't matter as long as it's consistent. It's where the amplitude is changing the whole time that you would have a problem. So again, with my conservation hat on, so much of this feeds back to the unnecessary replacement of mainsprings. Really, if there's one thing I can do before I leave this mortal coil, it's to try and encourage people not to replace mainsprings when they're set without trying them first in the clock, checking for depthing and bushing and all those things first. The second question, so I think the answer is, Chris, as always, much more research needs to be doing, and please try not to perpetuate the kind of the things that are written down in some of these books that were written in the 1930s. Some of them are absolutely brilliant, but there's a lot of stuff there, like George Graham invented the deadbeat escapement, which you still read today. It's probably on Wikipedia, which is not true. Anyway, Devashish says, how do you increase the supplementary arc? Is a clock with this problem? Okay, so if you've got a clock that's running right on your escaping arc, so it's basically only just running, there are two things I would say there. One, is it designed to be like that? Like a regulator, an astronomical clock is designed to run with a really small arc and really small supplementary arc. Some of them, you look at the escapement and it's just tiny, the amount of supplementary arc, but it's there because the maker of that clock was trying to keep the overall amplitude really, really small to avoid circular error. Circular error is negligible at small arcs. So that's why regulators, apart from Harrison's, typically have a small arc. So that's my first question. Is the clock actually designed to be like that? What I would do is I would draw out the escapement on CAD, or like I did last week on paper, if you don't have CAD, to try and figure out the angles. But if it isn't, then is there sufficient power getting through the, you probably have done this, but what I would do is so here's the actual clock pendulum with our rating nut down here, and it's swinging like this. Stick a bit of paper behind the clock pendulum on the back of the clock case or something, or on the wall, and just start the pendulum swinging tiny arcs until it just ticks. Then put you've really got a thing here, put a mark here and a mark here. That's your escaping arc, and see how much extra you get, your supplementary arc. And the answer is, it only has to be enough. Now, if you think that's too small, if it's tiny and the clock's going to stop, let's say the wall shakes a bit or somebody slams the door near to the clock. Sorry, take that back.
The pendulum has a tiny anchor and wider swing.
Yeah, well, it could be if it's an early clock with a tiny pair of pallets, then that's how it was designed and that's how it was made, and I wouldn't worry about it if it doesn't stop. If, though, it's a modern clock, we talked about the Smith's Enfield again. Why do these clocks have whopping great big strong mainsprings? Well, they have those mainsprings. That means that you can go to the retail jewelers, you can buy a clock, you can put it under your arm, take it home, you don't need a clockmaker, stick it on the mantelpiece, and it runs for X years, decades, and then you chuck it away probably. So it doesn't matter if it's out of beat, doesn't matter if the cat's sleeping on it, doesn't matter if it's wobbling a bit. But typically a lot of 18th and 19th and 17th century clocks are not like that. So the first thing to do is to take a long, hard look at it. Is it meant to be designed like that? Secondly, is somebody obviously bent the pallet frame? We talked in the previous weeks, never, ever, ever bend the pallet frame unless you think it's been bent before and you're bending it back. And the third thing is, if you say, no, it all looks as it's meant to be, but there just isn't enough supplementary arc, then, and the angles are correct, you can draw them out now because we've seen how you do that, then there's just not enough power there. You know, if you keep reducing the driving force of the clock, then you'll find that eventually it'll get down to escaping arc and it'll stop if you take more power off it. However, bushing, don't do bushing without depthing. What we find is that people put heavier and heavier weights on clocks or bigger springs because they think that that's going to solve the problem. In your car, I don't know anything about cars, but you can turn the radio up a bit and put your foot on the gas a bit more and forget about whatever noise is happening under the hood. Doesn't work with clocks. If you've got a depthing problem, you'll put on more weight. So you'll sometimes, it's not ironic, but whatever it is, find that if you reduce the driving weight, you actually increase amplitude. So it's quite a complicated problem. First step is it designed like that? Second step is, has it obviously been changed? And the third step is there a depthing problem, I would say? And please, in the chat, let us know what you think. So that was a bit of a rant to explain why pallets have got curved surfaces on spring clocks. It's to reduce escapement error. And you can, if you don't believe me, which I know you probably don't, get your weight-driven clock and put some more weight on it, and it'll start gaining if it's got an anchor recoil escapement, and it should start losing if it's got a deadbeat escapement. Right, gosh. Right, slightly shocked now after all that. Last week, we had our test stand. Oh, that's it. I remember now. Got our test stand here, look. And let's just see if we can. Oh, yeah, one more.
Divish says, doesn't moving the center distance also indirectly change the supplementary arc?
It will a bit. This was part of the question, actually. Thank you for reminding me that somebody asked in the week. Is it to do with the depth of the pallets? And the answer is the pallet should be set as we're doing here. So you've got absolutely minimal drop. So yes, if you take the pallets, if you move the center distance between the pallet arbor, which for new people, and sincere apologies to new people, we're not normally talking about math because you probably gathered in geometry, it's not my strong point. But if you change this distance here from the pallet arbor to the escape wheel arbor, which is here, that value, if you increase it, yes, you'll decrease supplementary arc because there's more energy being lost in drop and noise and heat and all that kind of stuff. But that's not the way to go. Set the pallets so the clock only just runs, as in the pallets, as deep as they'll go. Then if you've got a problem with supplementary arc, that's something else altogether. Don't try and sort of regulate the action of the escapement by changing the depthing. The depthing should be minimal drop, which I think we kind of, it brings us right back to where we started, if that answers the question anyway. So here's our clock. Let's put it that way around. Here's our little clock. And you will remember that last week we were talking about getting the clock in beat and setting the pallet. So I say this every week, that normally I would wear gloves when handling a clock, but it's too tricky with the camera and all that stuff. So apologies for that. So you can see here that this Smith's Enfield mantle clock, the back cock, which is this component, the screws are not round holes. I don't know if you can see that or not. Let's just see how we're going for focusing, but they're elongated, okay? And they're elongated so you can adjust this center distance. So the distance between the pallet arbor there, just about see it peeking out behind the escapement, behind the suspension spring, and the escape wheel arbor here. And as you draw, if you reduce that center distance when you're setting up the clock after cleaning, then you'll get to a point eventually where the clock escapement jams. And you know then you're right in the zone because the perfect working position is slightly further apart than that. So if we just get this thing ticking here, and maybe it's time actually to have a bit of a comfort break and to change over lenses. Oh no, it isn't, because I want to show you something else first. You can see that. We'll go back to this later, but I've just reduce this center distance by rotating the pallet arbor down. It's still fixed on by this screw here, and now clock's not running, the escapement's jammed. Now you might think that's really bad because your clock's not working, Matthew, but I know that it's right next door to being perfect. So all I do is I increase the center distance a wee bit. There we are. And our escapement ticks again with minimum drop. So don't set your clock up with lots of drop. The whole point is the drop is within reason. And again, John and I, we kind of joke about people who are obsessed by drop and look at the drop on that. And the answer is, you know, this kind of clock, you're likely to be able to get the drops right down because it's a machine-made clock. It's not had much hammer. Whereas our clock with the rogue tooth, which is tormenting me from across the other side of the studio here, the escape wheel's eccentric. So we will eventually get back to that. But one thing I noticed on this clock, and we asked, somebody said a few weeks ago about topping the wheel. So if you're listening now, then I'm just going to talk about that a little bit, because this clock wheel has got bent teeth. The ends of one or two teeth are just bent a little bit. So I'm going to quickly cover that, then we'll get round to putting the thing in beat. So remember, before, you might have noticed eagle-eyed people that they have already taken the two top nuts off the frame here. The bottom ones are still there, but the top ones are off. Bit dodgy. But, you know, when did I ever do anything that wasn't a bit dodgy? So I'm going to let the power off. Always got to let the power off with our let down tool. Don't use a key. And I would say, don't use it, you know, the clock's winding, keep this. And I would also say, I would get one of those let down tools, because if you use the key in a bit of wood with a slot, there's still that chance that it could slip out. I know people like those things. Personally, I would say buy the proper tool for the job because it's not worth it. So once we've done that, let's just quickly whiz our pallets out like this. So our pallet lifts out as an assembly, just pop that to one side. And because we've got our this incredibly convenient cutout in the frame here, normally you can't do that, but what I can actually do here is just to spring the frame a little bit, he says, and lift out the escape wheel, which is dead convenient. And the rest of the wheels, never spin the wheels like that, by the way, are still in the frame. So that's good. So our escape wheel here, what we've got are a couple of teeth that the ends of them have just got bent over. Now that could be me handling the thing. It's these clocks have been in bits for ages and ages and ages. And so very quickly, just want to talk about how you go about straightening these escape wheel teeth. Now, if you've got a lathe with a dividing head or a milling machine with dividing, your life's kind of easy because you can index this round. I think these have got 44 teeth on them, and check them against some reference. Most of us don't have that, but looking through a powerful eyeglass or a microscope, you can pick out rogue teeth. I think I showed you, I don't know if it was on this channel or the other one, making a bit of brass that just goes between the teeth as a little gauge so you can see which ones are bent. And then use a pair of pliers. Flat nose pliers, something like this, with smooth jaws. Really important that the jaws are not those ones with the kind of checkering on them. So smooth jaws. And rather than trying to actually bend the teeth back into position like this, the best way to straighten them is just to draw them out. And sorry, this is a bit of a long way away here, but just to go around them and just tease them out. And that will very gently straighten those bent over teeth. Now, the problem with doing it like this, or the other thing that it raises, is that if that tooth is particularly bent, brass work hardens. We know that. So from its annealed or soft state, if you bend it or you hit it with a hammer, it gets hard. So if you imagine our tooth, we bend it over, that one side, this side gets compressed, the other side gets put into tension. So that's going to be work hardened. So when you bend it back or draw it back in this case, it's going to be slightly longer because the bit that was in tension is not want to compress again the same amount. So the thing is going to be ever so slightly longer. topping teeth, again, I think it's one of those really nice kind of rite of passage things, and totally get it because it's a lovely idea. But on our other clock with the eccentric wheel, that topping the wheel is not going to help you. It's just going to make things a lot worse, because what you'll end up doing is taking teeth off at least half, if not all, the wheel, and it's still going to be eccentric. So the effective gap or the pitch of the teeth is going to change, and the clock's still going to run in and out of beat. The other thing about topping the teeth, can't find a clear bit of paper now. So here's our tooth. When the tooth is new, there's always this little bit on the top called land. The tooth can't be pointed like that because it'd have no strength and it would just bend over. So we have a little bit of land. Let's say it's 0.15 of a millimeter. If you top the tooth, and what topping means is basically cutting off or grinding off the tops of teeth to make it sort of round again, then of course what you're doing is you're increasing land, which is fine, but the challenge is that land equals drop. Your escape wheel tooth and your pallet have to move in relation to one another, at least by the amount of land you've got. So topping can get you out of a hole, out of a problem, if you've got 1 or 2 or 3 long teeth. Okay, topping's great for long teeth. It's not great for getting a really mangled up, poorly divided or distressed old wheel back in shape. What I've found you can do, just get my, happen to have my wheel topping engine here. What camera's in the way? What I've found is that if you've got let's say you've got a 19th century tall case clock wheel like we've got in our other project, and we've got everything going on there. The wheel's been damaged, it's got bent teeth, it's got long teeth, it's got short teeth, some are relatively poorly divided. Then 2 things you can do to rescue it before you've got to kind of write it off and make a new wheel. Got more questions coming in.
Dave Ashish
Yeah.
says, wouldn't teeth elongate?
Yeah, exactly.
Right.
Yes, they will. For the reason I've just explained, they get work hardened, so they stretch out. Well, strangely, if you try and bend them back, it's really difficult to get them straight, and also they seem to me to tend to break off. So I would just draw them out, maybe with a pair of bronze tweezers. But yes, they will. Hence this process.
And Sam a bit earlier said, does your escapement have a little lever on it?
Sam's very observant. Yes, Sam, it does. My escapement, I've drilled that pallet arbor and put that little lever on it. Yeah, well spotted. Sorry, can't possibly tell you why that is. Trust Sam to see it. So let's just put our camera on manual focus so we can get it in focus. So I'm just going to demonstrate topping this wheel. So that's basically shaving off, grinding off, cutting off those teeth that I've just teased out. You're absolutely right, Devashish. They are going to be, I think, let's say for sake of argument, fractionally longer than the rest. So we want to shorten them a little bit now. So when you're topping, as tempting as it is to get your hard-hinged lathe out and stick the wheel in there and wind a cutter into it, there's a chance if your cutter's really sharp and your lathe's going flat out, you might be all right, but that's kind of quite risky. So what I prefer to do is, having lost all the parts, is to actually stone the here we are, stone the top of the teeth with an Arkansas stone. And so I'm going to rotate so the wheel is going in this direction, so the tooth tips are trailing. And secondly, I'm going to have it rotating like this. So if there's any chance of it grabbing, it's going to eject the stone. What you don't want is going like this to drag it in, because it'll wreck the wheel. So I might wreck the wheel. So let's, this is a bit of a quick demo, but could be fun. So apologies to my lathe. Let's just get that right on there if we can. There we are. Good. I'm going to put my stone under there. But the problem here is, I should put a bit of paper on there, is that the stone isn't touching the wheel. So I'm going to get my trusty wooden wedge, framing wedge. These are really, really useful bits of kit. Get them from the DIY shop. So I'm going to use that to control the depth of the stone. So let's just, if it's thin enough, I am anyway. Yeah, it is. So very kind of gingerly, I'm just going to slide this under here, and I can find the point where I know where it's touching. So I don't want it to touch. So all I'm going to do, check it's going in the correct direction. Because the good thing about the Arkansas stone or the ceramic stone, of course, is because it's pale coloured, you can immediately see where the wheel touches the stone. And another, he said, duty bound to say, because we cleaned in mineral spirits and we haven't kind of finished the wheel, you can also see the points where the stone touches it because they'll be bright. So need a bit more wedge. So just move that back and move that down. Can you hear? Just starting to catch the longer teeth. I won't do many. So what I would say here is if you've got an escape wheel that is driving you bonkers because it runs in and out of beat, top up to about 1/3 of the teeth. So if you can deal with the 3rd worst lot of teeth from a height perspective, remember the relationship isn't just height, it's pitch and concentricity, which is also linked to height, of course. If you can top the 3rd worst, I would have said top actually 3, 4, 5 teeth if you can, and you can redivide the 3rd worst, they might be totally different teeth, then you're going to get that wheel back into the ballpark for an historic clock. If you find yourself having to top, like say, a half and redivide a half, then the chances are that that wheel, you've got a big rescue job on your hands. You can always, if you do find you have to top and those lands grow too chunky, then what you can do, of course, is you can cut some material off the back of the tooth to reduce drop and reduce land and therefore reduce drop. If you get into that situation, then you're probably heading towards kind of making a new wheel, I imagine. So if that, yeah.
Derek says you stone with the escape wheel going in the opposite direction to normal rotation, do you?
It doesn't matter, Derek. The question is, do you stone with the escape wheel going in the opposite to normal direction of rotation? It doesn't matter. It depends whether it's a deadbeat escapement where the teeth are facing forwards or a recoil escapement like this where the teeth are facing backwards. You want so here's our stone. You want to be going in this direction so they're trailing, because if they're going in this direction, it increases the chance of them digging in. So nothing per se to do with the direction of rotation when the clock's running, but you want to be going in this direction. And I had my stone wedged like this on that bit of wood. So if it caught, it's going to eject the stone. Whereas if we had it, let me think, going like this, in fact, if it caught, it would drag it in and damage the wheel, if that makes sense.
And David Bell says, would you under power or not?
Yeah. If you don't have this, you probably haven't seen. Some people haven't seen this arrangement. I'm just using a hand wheel. Zoom me out. There we are. So I am using Matthew power. But yeah, if you've got this is a thing. I've seen many a disaster with topping wheels. If you're going to do it under power, then you might actually want to go for a completely different approach. If you're going to use a lathe tool, you want lots of top rake on that tool, and do you something like that? But it's got to be really, really sharp. And you might actually want to just have the lathe going flat out, because if it's going slow and you feed too much, then it's going to bend the teeth off, I would imagine. So 2 approaches. Really, if you've got a scrap wheel, then practice beforehand, because it's a bit depressing when the thing breaks. Right. Well,
is that a clockmaker's story?
No, it's just a lathe. That's 8mm lathe, but I just use it with one of those large cast iron hand wheels. Yeah, just a regular 8mm lathe, which is really useful. So I'm just going to put my wheel back. Of course, as always, totally running out of time, but I'm going to carry on regardless. Put that wheel back. Might have to put some glasses on. Glasses, in fact. Yeah, I like the hand wheel. I've got a bit of a phobia about those sewing machine motors. When I first went to college, all the watchmakers' lathes had those little sewing machine motors, which are absolutely fine, but they had no speed control, so they would just be going, you know, a bit like a dentist drill. And the problem was that made it really difficult for students. We've had plenty experience already on this quite young channel that if you want to do things like drill hardened arbors, unless you're using tungsten carbide, even if you're using a carbon steel drill, you want to actually run dead slow. And same for using your graver on brass. You can easily get into the situation where the things just get in work hardened. So the answer, long answer, is I think those large hand wheels are brilliant. I mean, of course, they're limited because you have only got one hand to use. However, there's also a thing that you can get like a sewing machine treadle. So you've got a thing coming up through the bench and you can operate it by your foot, which is really useful. So let's just set this up and I'll just check that the pallets or whatever they're called, they're not just going to spin around. Great. Okay. So the next thing we're going to do, running out of time, we'll carry on next week, is to just set up the escapement. I'll do that first, this way around, and then we will just have a little change of camera position. Bear with me a sec.
Could you use a multi-fix motor?
Derek's obviously teasing me. You could use a multi-fix motor, Derek, and if you want to donate a multi-fix motor, contact us in the live chat and I'll send you our address. Multi-fix motors are, for those people, are like dead posh. Oops, we've got a wiring situation going on here. Super dead posh motors that are really nice because they are sort of variable speed and things. All sorts of problems here. I realized the other day that I'm actually not a clockmaker anymore. I'm a sort of some kind of digital animal. Right, okay. So we can now see that our escapement is in the joyous position, I think not showing anything too crazy, of not working. Yeah, we're agitating the pallets or moving them backwards and forwards, and we can see it doesn't run, which is great because we know now from our book, which is partly obscured by the camera, that all we need to do is to increase the center distance without letting the escape wheel run through, and it will begin to tick. Let's just, it's gotten slipped down. So I've just, there we are, just moved the body core somewhere. Get that thing off there. The pallet arbor up, and you can see now the clock's ticking, but we've got quite a lot of drop. So now we're going to move it back in the other direction of closing that center distance. I'm not going to move the clock around again. I'm just going to try and do it like this, which may be difficult. Close it up a little bit. You see the drop has reduced now. I mean, maybe the frame rate of the camera doesn't really show it. So I'm trying to find that joyous position too much, where it only just ticks. It'd be a heck of a lot easier to do it. Okay, so let's say we've faffed about with it and we've got it to the point where it only just ticks. Minimum drop, that will call the ideal position of our escapement. The next thing we're going to do, and it's a question we maybe next week now, but it's to set the clock in beat. So let's just put the pendulum on. There it is. Knew it was there somewhere. That's not too bad. I'll put it out of beat to start with. Just go on mute for a second. Mute, and I don't know whether you can hear that or not. It's probably still really quiet. If you can hear it, then you will hear that the period between ticks, or between a tick and the talk, is uneven. But you can see it probably more than you can hear it. You can also interestingly see those teeth that I've just topped going by, the ones that are glinting. So a question people say is, I should really put those nuts on the frame as well. How do you put a clock in beat? Or how do you know which way to move the pendulum or the crutch? So what is in beat? Well, the beat is the relationship, or the position for the relationship in terms of rotation between our escape wheel and our pallets when the pendulum is hanging, let's say again, at that point of rest. So to change the beat of a clock, 7 o'clock, what we do is we first have to determine which way this relationship between the pendulum at rest here and the pallets needs to move. So one of those pallets is spending more time out of engagement than the other one in relation to the escape wheel, basically. And it's one of those things, as you begin to just look at it, and then you will kind of figure it out. But a little trick, especially with a mantle clock, is to lift one side of the clock slightly and then the other side, and see if that improves the situation. So I'm just going to do that now. So I'm lifting this side of the clock. And I can hear that the clock is now in beat. So what I need to do, obviously, this pallet, therefore, needs to be, when it's running normally, further into the wheel. So this clock, the Smith Enfield, is fitted with a friction clutch here. So normally, like on a 18th century, 17th century, 19th century long case clock, that arrangement is solid, and you have to bend a piece of metal, the crutch or the leader, I think it's called in the States, to change that relative position. In this case, the manufacturer has fitted it with a clutch, which is really cool. There we are. And so all we have to do, is it all, is to move the pallets or the pendulum to one side. And then if we can feel, if you can see, but there's a like an addition on the pendulum that's just banking here on the frame. Now that's designed so the pallets don't bottom out in the bottom of the escape wheel and damage the wheel. So we move it to one side until resistance is felt, and then move it a wee fraction more, and then try it again. So I moved it too far. So back a little bit in the other direction. There we are. I don't know whether you can hear that, but it's now pretty much in beat. Now, there's much more to say about drop, because as you can see here, the problem we've got is that the drops are uneven. I think there's more internal drop than there is external drop. That's like not exactly another life, but maybe we can tackle that in a another kind of stage of this thing. But for now, what we've achieved there is we've reduced drop as much as we can for this escapement without bending anything, so we get maximum efficiency, minimum noise. And then we've tightened these two screws, and we've put our clock on our mantelpiece, and then we've set it in beat. Of course, I'm having my leg pulled, teased at the moment over the test stand, but you'll be delighted to know that this is the last time we'll see the test stand, because I've got the case here. Yay, Chris is jubilant. I've got the case here. I'll just move that to one side, and then we better call it a day. Oops, sorry, microphone. Wrong lens now, but we've got the case. And what I've done is, of course, like a good clockmaker that I am, I'm not going to put my clock on test. I believe it's going to be fine. I don't anticipate any problems with it. It's going to go straight back in the case. But the case has been cleaned out, vacuumed, one of the first things we do. And sorry, we're on the wrong lens now, so we'll just maybe hold it up here. But maybe I'll talk next week about the treatment of the case. Now, I'm not obviously a specialist conservator with this stuff, but it'd be quite interesting to talk about that. If you follow us on Facebook, you'll have seen that I did a French clock marble case during the week, similar kind of treatment, really straightforward. So maybe that's where we should start off again next week with the treatment of this case, Bakelite. And also maybe next week we'll get on to the second part of that question from our person that bought a clock with no pallets. Hopefully we've dealt with the pallets now for at least the time being, but that clock also has no pendulum. So John has been pulling his hair out, trying to teach me some algebra of how to figure out the length of the pendulum. And I can tell you now, we're gonna get through it. It's gonna be incredibly painful like the pallets were, but we've got to get to the other side of it. So let's get the clock recased, and then nice bit of Bakelite there. Was Bakelite, by the way, a bit of homework for you? Some of you will know, was it shellac lacquered when it was new to make it shiny, or did it just come out of the mold and it was shiny? I don't know, maybe some people out there collect radios and things. John does, I know. But anyway, so we've got a pendulum length theory lesson coming up, I'm afraid, and then eventually we'll get back to the other escape wheel tooth, which we've got to get escape wheel, which we've got to get off its collet. So lots in store. Thank you for bearing with us today. A bit of a marathon. Hope that was useful about escapement error. Do some experiments at home with your clocks that you're working on, and think again about that pushing before or retarding before or after the line of centers, because once you get that, it'll make a whole lot more sense about replacing mainsprings, and also about the performance of spring-driven clocks, and why the fusee, of course, was invented and applied to clocks. So thank you very much. Big breath. I forgot to mention today, again, was the Antiquarian Horological Society AGM. So it's been like a whole day of horology, and that was brilliant. So shout out to those people. That was very cool. Thank you for all that was involved. And we'll see some of you on Thursday. It's open to all, our live stream on repairing a long case clock. Say hello on Facebook. Thank you again to the Facebook people. And most of all, massive thank you to Team Open Clock Club here, who's been typing away like crazy and feeding the questions. So have a great weekend, everybody, and we will see you very soon. Bye for now.